Okay, so we are from Ericsson, and now we'll be presenting our work, actually just giving an overview of our work, what we did in the memory management, so how we enhance the memory management of DPDK, and yeah, with my colleague we will be just giving you that. Okay, so yeah, so actually, I mean, here it looks like the world is changing because the ground is not stable under us because like we need to live in this cloud environment, and then we're not just building something which runs on a specific hardware and hard coding things over there. And so we need to adapt to these various requirements. So basically, I mean, what we need to tell is that we are developing a platform for applications, and we have many types of applications, many different types of applications running in a container, I mean, running in VM containers natively. So we need to support all these different environments. So usually, I mean, the problem is that there are many, I mean, applications have different requirements, like what to support, performance, security, footprint, robustness. So these require different types of memory. So if shared memory versus packet copying and things like that. And we have these native containers, VM, unikernels, x86, ARM, so different architectures we need to adapt to. So we cannot just hard code things. And so that's why we need an abstraction layer. I mean, that's where we're all coming from. Like, we started to support these types of applications. So yeah, so this is valid for the interfaces, queues, everything, not only the memory management. But now we're just focusing on the memory management part. So currently DPDK has some limitations, as Bruce mentioned in the earlier presentation. Like he explained, gave an overview already what are the current problems. So we have like one big problem is the static allocation. When you start DPDK, it allocates memory, and then later on you don't have a chance to add more memory to the DPDK if you need, and it basically grabs all your required huge pages. And then memory initialization takes a very long time, and so because of like if you want to use a huge memory area, just collecting the huge pages, zeroing the huge pages, that takes a long time, and people are complaining that we are even zeroing if it's not really needed. So, and again, the same problem like the physical memory dependency, which now with this new type of memory management it's gonna improve, and yeah, basically no support of these different types of memory management. So now we're just trying to, like this is just an overview of how DPDK works. So it grabs all the huge pages and at startup, and then if you're running a multiprocess environment, I mean multiprocesses, then they just attach to the memory, and then it's again just initializes the memory. So yeah, just a sequence of how it is done. So basically, you just in a primary process you allocate the memory, and then while it's doing the allocation or init time, the other process is just sleeping, and then when the primary process releases the lock, then it just attaches to the memory. Then both processes start allocating memory, and there is a lock inside the memory allocations. So then two processes start fighting with each other. So yeah, so basically, I mean, this is the problem. Like, we have no isolation, no memory protection. So this is mainly a problem for a multiprocess environment, and no fine-grained control of the object placement. So you cannot tell that I want to place my object in a specific place. So it will become clearer probably then. So now I just give the word to Tom to explain the enhanced memory manager.
Good afternoon, everyone. My name is Tom from Ericsson. Next, I will introduce how we designed the enhanced memory manager to solve all the problems mentioned by Laszlo just now. So as you can see, this picture, this is the overall architecture of the enhanced memory manager framework. So over the top, we have the applications. In the middle, we have the DPDK. At the bottom, we have the enhanced memory manager. Both the DPDK and the enhanced memory manager will be used by the application, since the different applications have different requirements on the memory. So DPDK could not fulfill all the requirements. DPDK will use the enhanced memory manager as well. We extend the DPDK memory manager to use the external memory. So DPDK will be a user of the memory domain. At the bottom, we have our enhanced memory manager framework. The top half is the memory domain. Memory domain is a named memory partition with a lot of features defined on, such as it's virtually contiguous, physically contiguous, the access control, its pneumotype, its size, its huge page size. And all these kind of requirements as a feature will be processed by the memory domain component and change the requirement into the memory request. So bottom half is the memory allocator manager. It is a general framework. We can accept different kind of plugin, such as the standard Linux huge page memory allocator will be a plugin we support, just like DPDK. And also we can support the glibc heap allocator, and also we can support the shared memory, the inter-VM shared memory. If one application wants to originate the communication with another VM, we can just define a memory domain to specify its requirement is need the inter-VM. So we can allocate the memory from the inter-VM shared memory allocator. So all these kind of memory allocator can be existing simultaneously. Just based on different requirements, we request the memory from different memory allocator. So generally, this is our proposal, the summary. So both the DPDK and the enhanced memory manager will be used by the application. We support the backward compatibility. That means we use the DPDK in the normal way. So applications can get the specialized required memory on demand from the enhanced memory manager to meet its requirement through the memory domain API. And we extend the DPDK to support the external memory manager plugin. And the enhanced memory manager itself is a framework. It can support different kind of memory allocator, such as today we already have the huge page, glibc shared memory, and inter-VM shared memory. So next, I hand over to my colleague Laszlo to describe the methodology behind this proposal. Thank you.
Okay, so basically the key is that, or the current problem is that DPDK, the memory management is tightly coupled with DPDK at the moment. So it's like you have, I mean, if you use a specific version of DPDK, you're pretty much stuck with that memory manager. You don't have a way to feed memory into DPDK unless you patch it yourself, which we want to avoid usually. So that's why our proposal is like, we would have plugins. I mean, that's just support external memory manager. We would have plugins, and these plugins could be developed independently. And then you can have support of many different types. And contribution is easier because anyone can contribute with their plugin to DPDK. So basically, this is just how we do this in what are the concept of memory. So like, we just describe your memory partition. Like you give an arbitrary name, main memory, and then you describe, you have different types. It's just an example, like you have a pneumotype, which is what DPDK is using. It's allocating pneumo-aware memory. And then policy static means that you will allocate when you initialize the memory. And then you just describe if you want how many 4K huge pages or 2 meg huge pages you want, or 1G or whatever way you describe. And then basically that's what is happening. Like when you start up your process, it will not initialize the whole memory. It will just initialize that portion. So you just tell DPDK that I want to be a user of the main memory, which is described there. If it's not described, then we can just fall back to the original behavior, which is, again, just a default description file. So you just describe the current behavior that way. So you just say attach to the main memory, and DPDK will only initialize that, and it will zero the memory if needed. So then you create, actually, when you bring up other processes can attach to the memory. So one can say that I only want read-only access, or the resource manager can decide that this guy only have read-only access. So then it will just be mapped as read-only in the other process. So it solves the multi-process problems. And then you just describe, you have another configuration like local memory. Type exclusive means that all of these instances will have their own memory partition. And then policy on demand can mean that you, whenever the application queries, want a new huge page, it just pops up on demand. You can specify minimum amount of needed memory. And you can say no zero true, which means that you don't want zeroing because its application is not relying on that. So you just describe what you need. And then the processes just say, so each process will just say attach to local memory. And then each of them will have their own partition. So that's basically it. And this is, again, a sequence like primary process. Both processes are started. So we just attach to the small portion, which could be 4K 2 meg. It doesn't have to be contiguous. It's just 4K, or depends what you want to use it for. And then process 2 just awakes, attaches to main memory. And then each of them, both of them can initialize memory on their own. And then you don't have fragmentation. You can keep control of the page, the TLB cache entries, if you like. So you have access control, placement control, isolation, memory protection. And basically, that's it. These slides are just, we don't want to go through all of these. So it's up to you. You can just look into that. Basically, we describe most of them. So the easiest way would probably like creating mem domains where you just, application doesn't have to tell that I want 2 meg or 1 G huge page. It just tells that I want fast memory, medium, and slow memory. So then it becomes very easy for the application. It doesn't have to be aware of the huge pages. So you publish on a specific environment. You describe what fast memory means, which might mean different on an x86 than on an ARM. So that's basically it. I hope you got the idea. And this is our previous work. So few of you might already seen our work, like we presented in the first DPDK summit. And so that's it, basically. Questions?
Question here. So this is going to be a library that you link to your DPDK app against, or is another process? So you need another core for doing the management?
No, this is basically a library, and you can just, so it could just be part of the DPDK, similar to the POMO drivers, where you just you can just place your plugin somewhere, and then DPDK can pick it up, and then you can just use it in a config. So this is basically just a library, and the execution comes with the, like when you execute EL in it, that's where it attaches to the mem domains which you gave to the application. If your application is a user of a mem domain separately of DPDK, just uses the API, and there's a shared memory database behind. Or a resource manager, there could be a resource manager somewhere running even outside in another VM, another container,
okay,
where access could be controlled. And
so is this flexible enough if you have 2 DPDK applications? No, multi-process, two different applications.
Excuse me, I didn't.
If you have 2 DPDK apps, not just one multi-process DPDK app, does it work as well? Is flexible enough for supporting this?
Yes, of course. That's the main purpose. Yep. So you can support multiple DPDK instances. You can partition, because we have, this is just about the memory management, but we have similar things for abstracting the CPU, the topologies, and the queues, ports, everything. So you can just describe. So you can just describe the requirements of one of your domain, we call them application domains, where you create or give resources like CPUs, memory to an application domain, and then you have another one, so you can bring up 2 DPDK instances.
So you define different requirements for different DPDK apps.
Yeah. It's just the idea is that
But
you have a publisher component which just publishes the configuration, and then DPDK.
But what I mean is, if there is a conflict, it's going to be the first DPDK app who takes the resources, and the other one is not going to be able to execute.
So it's harder.
If there's a conflict between the configuration that you have for the 2 different DPDK apps, what is going to happen? The second app is not going to be able to execute, or?
What do you mean in conflict? Like you describe requirements of one application domain, and then they can, application just attaches to that resource. So both of the applications can have rights to attach. So even in this way, you can even create shared memory in between 2 application instances, and you can consider it as a resource manager component running underneath, which might still just be a library and a shared memory database. But you can have your own daemon running if you like.
Okay, thank you.
All right, to keep the program going, we may have to move on, but these guys will be around, so at the break, maybe catch them, and
Yeah, sure.
thanks very much.
Thank you.
Okay.